This video is brought to you by mywayteaching.com.
So in this part, let us study about the rolling friction. A body like a ring or a sphere, you can consider any of these two. Okay, the rolling without slipping over a horizontal plane will suffer no friction, isn't it? So when we consider a ring or a sphere which is rolling without coming in contact with any of the horizontal surface, it experiences no friction. In principle, at every instant, there is just one point of contact between the body and the plane, and this point has no motion relative to the plane. In this ideal situation, kinetic or static friction is zero, and the body should continue to roll with constant velocity. But we know that in reality, this will not happen, and some resistance to motion does occur. Yes, even though it is not in contact with any horizontal surface, there is some resistance to that moving body, or which is the to that ring which is rolling, isn't it? So to keep the body rolling, some applied force is needed. For the same weight, rolling friction is much smaller than static or sliding friction. So this is the reason why discovery of wheel has been a major milestone in human history. So rolling friction, again, it has a complex origin, though somewhat different from that of static and sliding friction. So here the force which opposes that roll, the rolling of a ring is nothing but rolling friction. Okay. So during rolling, the surfaces in contact get momentarily deformed a little, and this results in a finite area of the body being in contact with the surface. The net effect is that the component of the contact force parallel to the surface opposes its motion. Okay, we often regard friction as something undesirable, isn't it? In many situations, like in a machine with different moving parts, friction does have a negative role. It opposes relative motion, and it thereby dissipates power in the form of heat, isn't it? So and lubricants are a way of reducing kinetic friction in a machine. So we always try to reduce that friction, isn't it? And one of the way that we follow is by using lubricant. So lubricant is the one way which is used to, or the lubricants are the way of reducing kinetic friction in a machine. And the another way used to is used to ball bearings. So you in vehicles we see this, isn't it? Ball bearings. So between two moving parts of a machine, and you can see that ball bearings in this figure A. Okay. Since the rolling friction between ball bearings and the surfaces in contact is very small, power dissipation is reduced. Okay. A thin cushion of air is maintained between solid surfaces in relative motion is another effective way of reducing friction. Okay, in this figure you can see a thin cushion of air is maintained between the solid surfaces in relative motion. Okay, that is also one of the way of reducing the friction. So in many practical situations, however, friction is critically needed. Kinetic friction that dissipates power is nevertheless important for quickly stopping relative motion. So it is made use of by brakes in machines and automobiles. Similarly, static friction is important in daily life. We are able to walk because of friction. It is impossible for a car to move on a very slippery road. So on an ordinary road, the friction between the tires and the road provides the necessary external force to accelerate the car, isn't it? So friction is very much required, but in some cases it's, of course, it plays a negative role. For that we have some of the ways to reduce it. So now let us study about the circular motion. So we have already seen that acceleration of a body moving in a circle of radius r with uniform speed v is given by what? V square by r, isn't it? The acceleration of a body which is moving with the velocity v in a circle of radius r is given by v square r, and its direction is always directed towards the center. We know this, isn't it? So according to the second law, the force Fc providing this acceleration is, so if you consider in according with the second law, then the force Fc which provides this acceleration is given by Fc is equal to mv square by r, where m is the mass of the body. So this force is directed towards the center and it is called as centripetal force. So this force is also directed towards the center, and the name of this force is centripetal force. Okay. So the name of this force is centripetal force. For a stone rotated in a circle by a string, a centripetal force is provided by the tension in the string. The centripetal force for a motion of a planet around the sun is the gravitational force on the planet due to the sun. Even you can consider a car. Okay, for a car taking a circular turn on a horizontal road, the centripetal force is the force of friction. So the circular motion of a car on a flat and banked road give interesting application of the laws of motion. So we are considering the circular motion of a car on flat as well as on a banked road. So how it works, let us see. So the first case is the motion of a car on a level road. You can see here in this figure. And the second case is the motion of a car on the banked road. Okay. So in the first case, that is motion of a car on a level road. So you can see here there are three forces that act on this car. So the weight mg and the normal reaction n and even the frictional force F, isn't it? So there are three forces that act on the car. So the first one is the weight of the car, that is given by weight mg, and the normal reaction n, as well as the frictional force F. Okay. So as there is no acceleration in the vertical direction, we can write n minus mg. According to the second law, we can write n minus mg is equal to 0. So in other words, n is equal to mg, since there is no acceleration in the vertical direction. The centripetal force required for circular motion is along the surface of the road, and it is provided by the component of the contact force between the road and the car tires along the surface. And this by definition is the frictional force. That contact force between the tires and the road is nothing but what? Frictional force. So note that it is the static friction that provides the centripetal acceleration in this particular case, and the static friction opposes the impending motion of the car moving away from the circle. So we can write F is less than or equal to mu s into n. We know this, isn't it? So that is nothing but the centripetal force in this particular case, that is mv square by r. So that is given by considering equations, that is already we have studied those equations, that is Fs is less than or equal to mu s into n, isn't it? And even we have studied one more equation, that is the centripetal force Fc is mv square by r. So we can write v square is less than or equal to mu s rn by m, that is equal to mu s r into g. So which is independent of mass of the car. So this shows that for a given value of mu s and r, there is maximum speed of circular motion of the car possible, and that is given by V max, which is nothing but the square root of mu s r into g. Okay. In the second case, that is the motion of the car on a banked road, we can reduce the contribution of friction to the circular motion of the car if the road is banked. Since there is no acceleration along the vertical direction, the net force along this direction must be 0. So we can write n cos theta is equal to mg plus f sin theta, isn't it? Since there is no acceleration in the vertical direction, we can write n cos theta is equal to n sin theta plus mg. The centripetal force is provided by the horizontal components of n and f. So therefore we can write n cos theta, so n sin theta in the horizontal direction, the n you can see here n sin theta plus f cos theta. These two provide the centripetal force. That is given by mv square by r. But we know that Fs is always less than mu s into n. Okay. Thus to obtain V max, we put F is equal to mu s into n. And then we can get the equation n cos theta is equal to mg plus, in place of Fs we are putting, yes, in place of F we are putting mu s into n. Mu s into n sin theta. This is for vertical direction. And in similarly in case of horizontal direction, we get n sine theta plus mu s into n cos theta is equal to m v square by r. Okay. So from equation these two, 1 and 2, what we just derived from these two equation, we obtain n. Okay. See, from this first equation, we can get the value of n. So by taking n common and taking this side, we can write it as mu s sine theta is equal to mg, isn't it? So n will become mg by cos theta minus mu s sine theta. So substituting the value of n in the second equation, so that is mg by cos theta minus mu s sine theta, we get sine theta plus mu s cos theta is equal to m v square max divided by r. In other words, we can write V max is equal to Rg mu s plus tan theta by 1 minus mu s tan theta whole raised to 1 by 2. So we can see that the maximum possible speed of a car on a banked road is greater than that on a flat road. So comparing this equation with the equation that we derived before. Okay. So comparing those equation, we can see that the speed of the car is more in case of a banked road compared to flat road, because in the first case Vmax was square root of mu s into Rg, but here Vmax is Rg mu s plus tan theta by 1 minus mu s tan theta whole raised to 1 by 2. Okay. For mu s is equal to 0, in this particular case we get V naught is equal to Rg tan theta whole raised to 1 by 2. Okay. So at this speed, frictional force is not needed at all to provide the necessary centripetal force. Driving at this speed on a banked road will cause little wear and tear of the tires. The same equation also tells you that for V less than V naught, frictional force will be up the slope and a car can be picked only if tan theta is less than or equal to mu s. Okay.